A video on day 3. Basically, the main thing is the degree of a graph. There's also a handshake problem if you looked at the chapter or the section. So we're talking about the degree of a vertex. So again, a vertex is just some point, and then what the degree then means is how many edges are touching that specific vertex. So you could look at it and you could see, for vertex 4 right here, it's right here, it only has one edge connecting it, touching it, so the degree is 1. For V1, vertex 1 right here, there's an edge right here, an edge right here, and an edge over here, so it has degree 3. Vertex 2, we have edge here, that's degree 2, and vertex 3 has degree 2 because those two. So each vertex has its own little degree, and a graph altogether, you just add up all the degrees from all the vertices. So the total degree of this graph is 8. And then these definitions are things that we've covered before: parallel edges, and loop, and isolated vertex, and a simple graph. So those are from the previous video, but we might use those still. Okay, so here's a theorem, and this is kind of important. The total degree of any graph equals twice the number of edges in the graph. So we can make one up if we wanted, like, just say we got vertex 1 and vertex 2, and maybe we got vertex 3. And however you want to do this, like, we can have an edge there. Let's put it in black. An edge there, maybe this has an edge, and just keep it really basic. The total degree of the graph then is twice the number of edges in the graph. So if you think about it, V1 has degree 1, V2 has degree 2, and V3 has degree 1. So count the edges, 1, 2, and then the total degree is 1 plus 2 plus 1 is 4. So there are 2 edges, and there's a total of 4. The degree 4. So what else? It leads us to a couple other things, in that the total degree of a graph is even, and that's like always going to be true, because we're doubling it, basically, the edges. You can always just double the edges. And then we also know that the number of odd vertices is even. So that's that's interesting too. So the number of odd vertices in this example over here is, you had this had degree 1, so it's odd number. This had degree 1, and that's an odd number. There has to be an even amount of odd degreed vertices. That's what this second corollary is saying. So then you could also test another graph. So just to make this more accurate, V2, I drew another line here to make it have a degree 2, actually. And then V3 is an interesting case because it has 2 that go to V2, so that's degree 2 right there. 1 that goes to 1, so that's total degree 3 of this vertex. But then it has a loop, and a loop counts as 2 because it uses its endpoint, this vertex, twice. So this loop is 2. There's 2 more edges right there, and then another edge is 5 total. So what the corollary number 2 again says is that even in this graph, there has to be an even number of vertices that have an odd degree. So vertex 1 has an odd degree, vertex 3 has an odd degree, and there are 2 of them. So we have an even number of odd degreed vertices. So that's one important thing that may come up. We should practice drawing some of these a little bit. So we want to draw a graph, or show that you can't. So we'll just see if we can break it, if we can't draw it, using the logic that we just found out about. So draw a graph that shows a graph with 3 vertices of degree 1, 2, and 3. So V1, let's say maybe it's right there, V2, and V3. I'm just kind of doing a triangle to keep space. So degree 1, let's say maybe it's this one. This one has degree 1. I can give it to either of the other 2, but that's the only edge that can connect V1 because it has to stay at degree 1. So maybe I'll go to V2. That's fine. V2, so I've used this one. V2 has to have degree 2 or 3. So I could say, I could make an edge go to here. Now it has a second degree. Or I could also say that maybe this goes to V3 again. So then we have parallel edges, which is fine. But this is now degree 3, which is fine. We get that one. And this one ended up being degree 2. So this graph works. And we knew it was fine because there was 1 and 3 degrees. That's an even number of odd degrees. So that makes sense. That was good. This next one is going to be a little bit harder because it's a simple graph. So we can't have parallel edges like this, and we can't have loops. So if we do the same thing, so it's because a simple graph can't have parallel edges or loops. So we could say the same thing, but maybe we start right there. Now the only way to get, we did parallel edges here before. We could give this thing a loop, then it has degree 3, and then maybe give this thing a loop, then it has degree 2. This would be degree 3 right here because of this edge, and then the loop counts as 2. However, then it's not a simple graph. So there's kind of no way. We got to avoid loops and parallel edges. So then maybe we'd have to draw a line there, and now we're stuck. I can't go back to 1. They'd all have degree 2 at that point, and this is supposed to be degree 1. So we can't really do it. We can draw a loop to make it have these degree requirements, but it won't be a simple graph then. Or if we did parallel edges like before, it would work, but we don't have a simple graph then. So again, simple graph is no loops and no parallel edges. Okay. Another thing is there's a handshake problem that we should talk about. And let's just say that we have, so this is referenced in the in the section. You have a person there, a person here, and we want to know like how many handshakes will there be total if everyone shakes hands with everyone else one time. So let's say this is person A for the first person. He shakes hands with that person, that person, that person, and that person. All right, so that gives us 4 handshakes. Oops. Then we say, maybe this person has to shake hands with everyone else now, but they already shook hands with this person, the first person. So not that one. Then we get this guy, and that guy. So there's 3 more handshakes that took place. Then let's see. This next person already has 2 handshakes out of the way, red and purple, but has to give handshakes to this person and to that person. So that's 2 more. And then you see these black yet, yellow's bad. So this next person over here, it has shaken hands with almost everybody else. There's only 4 other people, and they've already given 3 handshakes. So just that last one. It's a terrible color. So 4 is 7, 8, 9, and 10 total handshakes. There is a formula for this, so you can do this instead. It's just n times n minus 1 over 2. So in our case, there's 5 people total, and then it'd be 5 minus 1, which is 4, divided by 2. 5 times 4 is 20, divided by 2 is 10 total handshakes. So that's just kind of the handshake problem, and it's pretty easy to understand. So notice, if everyone else shakes everyone else's hand, what's their degree? So this person here, 1, 2, 3, 4 edges, 4 degree. This person has degree 4 as well. Degree 4, degree 4, degree 4. Okay. Just a forewarning. Because then what happens here is how many handshakes are needed in a group of 15 people if each person is to shake hands with every other person. And so you just use the formula 15 times 14 divided by 2 ends up being 105. Is it possible in this group of 15 for each person to shake hands with exactly 5 others? Please explain. So it's exactly what I was saying with that degree. You have to have an even number of odd degrees in any graph. So if shaking hands is like edges on a graph, you have 15 people. Every vertex then, if each person in 15 is going to shake hands with exactly 5 other people, then each degree is 5. And that could be okay, except we have an odd number then of every vertex having an odd degree. So we have every vertex has degree 5, and there is an odd number of vertices, so no, you can't, because that's against the corollary saying that every vertex has to have an even number of odd degrees in the total in all of the vertices in the graph. And then is it possible of this group of 15 for each person to shake hands with exactly 6 others? And then there's really nothing to say against that. The total degree has to be even, and there are no odd vertices, so it ends up working out. And we can do this. We can make some proofs. I must have done this before, but so that's the main thing. Is that the questions are typically about the degree of a vertex, and the corollary right here is also important.